Continuing with L by D ratio. If the L by D ratio is small, then the film force is lesser, obviously, because the area that we see right here will be very small. So therefore the film force will be very small, and therefore we need the bearing naturally has a lesser load carrying capacity. However, the advantage with a smaller L by D ratio is that you can have larger misalignment, and also the heat that is generated because of friction is also very less. This can be again seen from this image right here. We find that the film area here is very less, and if the film area is less, the heat that is generated from this area will also be lesser, and also it is much easier to go ahead and cool such a small area. So lesser L by D ratio has lesser load carrying capacity. However, it allows more misalignment, and also heating is not at all a problem. Heat dissipation becomes very easy with these kinds of bearings. The next important parameter which affects the bearing performance is the bearing clearance. The diametral clearance affects the performance of the hydrodynamic bearing in a very significant way. So what is the main criterion? The minimum clearance should be such that a continuous lubricating film should be there between the journal and the bearing. Okay, so journal and the sleeve should have a continuous lubricating film, and if a continuous film has to be there, therefore the clearance should have a certain critical value, and if the value of the clearance is less than the critical value, then obviously there will be semi-liquid friction. That means there will be contact between the two surfaces. That is certainly not required. However, if the clearance is greater than the critical clearance, then we will see that the bearing works in the liquid friction domain. We will look into the expressions in the coming slides, but another very important aspect of bearing clearance is its relation to film force. So I pose a question to you. Suppose there are two conditions. Condition one is that you have a very thin film bearing. It is continuous film, but the clearance is very small, and on the other hand you have a very thick film bearing. So when I say thin film bearing, I am assuming that there is complete separation between the two surfaces. So that is assumed. On the other hand, I am saying a thick film, there is separation, but that separation is of large value. So considering these two cases, in which case do you think will the film force be larger or the load carrying capacity be larger? Will it be larger when the film thickness is small, or will it be larger when the film thickness is large? This question, to answer this, requires a little bit of insight. The answer is that if the film is very thin, the load carrying capacity is larger. Now how does one get a rationale for this? The answer is, if you have a very thick film bearing, that the oil film is very thick, it acts like a damper. So therefore if there is a very large load, then that load will cause the film thickness to reduce. On the other hand, if the film thickness is very thin, then the load carrying capacity is much larger, because the thin film acts in a much more rigid way. So the bearing clearance affects not only basic bearing performance, but it also affects the load carrying capacity of the bearing. Now let us see what should be the value of the critical film thickness, the film thickness which distinguishes between semi-liquid friction and between the full liquid film lubrication system. So it is given by this formula, that is HCR is RZB plus RZJ plus YO. Okay, so now let us see what are these points, and then I will explain graphically what is the significance of these values. So RZB is height of the micro irregularities on the bearing surface, that is the sleeve surface. RZJ is height of the micro irregularities on the journal surface, that is the surface of the shaft. And YO is nothing but the deflection of the supported length of the journal. So this deflection is also considered, and because of this deflection, it should not happen that the journal in the bearing or the journal in the sleeve are touching each other. So therefore, a summation of these three contributes to HCR. And if the actual film thickness is greater than HCR, then obviously we will have complete liquid friction regime. Now let us try to understand what is this RZB and RZJ with the help of a graphical illustration. RZB and RZJ can be visualized from the following diagram. Now consider these two to be the different surfaces. So this is the surface of the bearing or the sleeve, and this is the surface of the journal. If we zoom into the surface from an external look may appear flat, but however when you zoom into it and see it under microscope, we will see that there are micro irregularities. So surface roughness is calculated based on this. So there are different parameters, the RMS value and the mean value. But what we are taking here is this value of RZB. RZB is basically what is the maximum height of the peak of the surface of the bearing. So if we see here, so this may be called as the maximum height. And then we also consider RZJ. RZJ is the maximum height of the peaks or asperities of the journal. So, so that is the maximum height. In between, we also consider this value YO, which is the gap that we have purposefully kept just in case the journal bends. So if the journal bends, then this gap can close. So therefore the HCR is the summation of these following things. HCR is summation of, first of all, RZB, RZJ and YO. So here we can see that if the film thickness is greater, if H is greater than or equal to HCR, we will find that this results in liquid friction. And if H is less than or equal to, not equal to, less than HCR, then that results in semi-liquid friction. And this is something which is not required for any bearing performance, because if there is semi-liquid friction, then we can find that it becomes very easy for the bearing to fail. Heat is generated, wear takes, adhesive wear, abrasive wear, different modes of wear come into the picture, and the bearing fails at a very fast rate. Moving with our derivation, here we see this is the value of HCR, and that is equated to the actual clearance value. So clearance value is nothing but difference in the diameters of the sleeve and the journal divided by 2. So this is capital D minus small d by 2, and that becomes equal to psi into d by 2, where psi is the relative diametral clearance, and the formula can be seen in the previous slides. However, it's quite difficult to actually go ahead and calculate and take the surface roughness measurements and estimate what may be the deflection. So in design, following approximate expressions are used. So one of the best ways is to simply double the height of the RZB and RZJ combined. So you just add the height of the asperities, the bearing and the journal, and then multiply by that 2. Multiply by 2, and that becomes your HCR. Moving ahead, there are different recommended values of psi for different bearing materials. If this value of psi is assumed for different materials, then automatically we can get the clearance value by just putting this value of phi inside this formula, and here you can get what is the critical value. So a tin based Babbitt has 0.0005 as psi value, which is d minus d by d, whereas aluminum has a psi value of the range of 0.001. Again, these are empirical calculations based on experience. So based on this, one can select what clearance he is using based on the material of the bearing, right from tin based babbitt to copper lead to aluminum. There are some more empirical expressions. Here is an expression which relates psi to the d. So if one has to choose a value of psi and he knows what is the diameter of the journal, then this empirical expression gives a value of psi, which can be again plugged into this expression right here, 5.44, and by which we can go ahead and calculate the HCR value. And also psi can be calculated based on velocity. There's a misprint here. This should not be y, this should be psi. Is 0.8 into 10 minus 3 into v raised to 0.25, where v is the peripheral speed of the journal in meters per second. Here we see some more recommendations of the diametral clearance for the different precision of machinery. For high precision machines, we have value of between 0.004 and 0.010, and for normal accuracy machines it becomes 0.02 to 0.03 millimeters. Another very important property which affects bearing performance is the viscosity of the lubricant. So viscosity of the lubricant is a very important phenomenon. In general, one can very easily understand that if one uses a very highly viscous kind of a lubricant, the load carrying capacity will be high. That is simply because of the density of the oil that is being used, and it is very difficult to displace that oil. So generally the load carrying capacity of higher viscosity lubricants is higher. On the other hand, if you have a very thin and less viscous lubricant, the load carrying capacity will be very low. So based on this, one can choose the lubricant. However, one has to be very careful in choosing the viscosity of the lubricant. If the viscosity of the lubricant is unnecessarily high, then apart from creating extra load carrying capacity, it also creates excess amounts of heat. Higher viscosity means higher internal liquid friction, so the heat that is produced will be very high. On the other hand, if one uses a very low viscosity lubricant, the heat produced is also less. So after having found the value of psi, the required viscosity of the lubricant can be again determined from this following formula, that is the mu should be greater than p psi squared by omega s naught, where s naught is again the critical Sommerfeld number. So if the Sommerfeld number is designed, then based on that one can go ahead and choose the lubricant. Now a question may have arisen that this formula is very similar to the actually it's just another version of the formula which we have seen earlier, and that formula can be seen in the previous slides, which is right here, which is omega 2 is p omega squared by mu s naught. So how does one arrive at the viscosity given the velocity, or what should one assume? So the answer is obviously one should have a good engineering sense and choose a certain viscosity first. Based on that, he will get what are the operational speeds, and if he sees that the operational speeds are beyond the range, then the viscosity can be adjusted, and so that one can achieve full film lubrication. But in this practice, always some kind of assumption will be required. So it is always a good practice to assume a certain value of viscosity and then go ahead with the calculations, and then make relative adjustments so that the bearing becomes optimized. And finally, after selecting all the other parameters, the most important parameter is the load carrying capacity and the load coefficient. So ultimately this is the purpose of the bearing. How much load can the bearing carry? The load carrying capacity of a hydrodynamic bearing is again given by this formula, where P is the load carrying capacity, which depends upon mu, viscosity, omega, the rotational speed of the bearing, psi is the relative diametral clearance, the L by D ratio, which is L and D, and also this coefficient called CL. Now this coefficient CL, basically these expressions are simplified versions, and because the derivations are very complex, therefore many coefficients are introduced so that the calculation becomes very easy. So CL is a coefficient which again comes from the basic theory of hydrodynamics, which obviously which we do not have time for right now, but we will see how this value of CL is used to determine the load carrying capacity of the bearing. The value of CL is found from the following table. The load coefficient CL for hydrodynamic bearings depends upon, first of all, the L by D ratio, and the second parameter is eccentricity. Again, so one may ask, where has this table come from? So this table is the result of the derivations which lead to actual calculation of the load carrying capacity of the bearings. So because the derivations are out of the scope of our current syllabus, ready-made these tables are made for the designer, and all the designer has to do, he has to select the proper values based on the input parameters. So the input for calculating CL is L by D and epsilon. So let us now understand what is this value of epsilon. The following diagram explains the eccentricity ratio or epsilon concept. So this epsilon is very important to calculate the load coefficient, and then the load coefficient helps us to determine what is the load carrying capacity. So that is why we are trying to understand what is epsilon. Now if we look at this, epsilon is defined as E by C, where E is the eccentricity ratio and C is the clearance. To understand this concept, please have a look at the following diagrams. So the diagram on the left consists of a bearing which is in the centric position. What do you mean by centric position? That means the center of the sleeve and the center of the journal are same. Okay, so in that case, the gap around this entire peripheral area is constant, and therefore that is called the clearance. This clearance value is very simple to calculate. It is nothing but D minus small d divided by 2. Okay, so that is the clearance that is existing between the journal and the sleeve. The next condition is the actual condition, and this condition is when the bearing is stalled, or basically is not moving. In this position, the journal basically goes and rests on the sleeve. So at this point, we can see that the center of the sleeve, which is given by this dot, and the center of the journal, which is given by this dot, are not concentric. So obviously if they are not concentric, that means they have a certain eccentricity. Eccentricity means away from center. So your E is what is the distance of the center of the journal from the center of the bearing or the sleeve. So here in this case we can say that the E is maximum because there is contact between the journal and the bearing. Okay, so this is called eccentricity. Now the clearance value is always constant. It depends upon the diameters of your sleeve and the diameter of the journal, so that cannot be changed. However, eccentricity values do change. Eccentricity when the bearing is under stalled condition will be eccentricity will be maximum. So here your entire eccentricity is equal to clearance. In this case, if you see very carefully, your eccentricity is equal to clearance, so it becomes C divided by C, which becomes equal to 1. So the eccentricity ratio in this case would be 1. On the other hand, if the bearing was totally in the centric position, then the eccentricity in this case would be 0. Why? Because the centers of the journal and the centers of the sleeve are coincident. So in this case, if you apply the formula, then the formula would basically say eccentricity ratio epsilon is equal to E by C is equal to 0 by C is equal to 0. So here we can see the eccentricity ratio varies from a minimal value of 0 to a maximum value of 1. And when the bearing is in the operational condition, the eccentricity ratio occurs between 0 and 1. So therefore we can say that eccentricity ratio basically varies. It is greater than or equal to 0 and it is less than or equal to 1. So that is the limit of variation of eccentricity. So from this illustration, we have found that eccentricity ratio varies between 0 and 1. And typically in operational conditions, one can understand that the eccentricity ratio would be closer to 1 than to 0, because if the eccentricity ratio is 0, that means there is no film force being produced. So the eccentricity ratio is typically close to 1, maybe at the range of 0.7 or 0.8, because the film thickness is very small. Now, based on this, if one knows what is the value of eccentricity, one can go ahead and find out what is the load coefficient. For example, if the L by D ratio is 1 and one is running a bearing at eccentricity ratio of 7, then we can understand that the load coefficient is 2.0394. What has to be done next is that load coefficient has to be entered into this equation, and from this one can find out the most important parameter is what is the load carrying capacity of a certain bearing. So in the coming video, we will be seeing two design problems and two design approaches from which all the different parameters can be estimated and the load capacity can be